Welcome to another issue of the soap opera of science. It has been decided, first of all, let me say that we're going to talk about a lot of people here, but I want to make sure that you understand we're honoring these people because they brought knowledge forward. Every one of these things that we'll discuss today was a silly mistake and sometimes utterly ridiculous. However, that's the course of science. It stumbles around for a bit and gradually converges closer to the truth. We have to believe that, and we have to believe that every process in science, no matter how stupid, is useful and brings us towards the truth. As long as we're honest and competitive with each other's scientific results, you keep trying stuff and you get to the answer. So it's been agreed by many scientific bodies that the most important sentence, if we could pass on one thing to another culture, it would be all matter is made of atoms. That this sentence is the most important thing. So we have to understand what atoms are and why this is so important. The ancient Greeks, the ancient Greeks had a they had a word that means cannot cut. It was atom, and MC Hammer, actually, a lot of people don't know this, but his song was originally titled Atom, and it was an homage to the ancient Greeks. But he had a speech impediment, and so when he was trying to say, can't touch this, I mean, did you think I said can't touch this? He was saying, can't cut this. Doom, doo, doo, doo. So the thing was, this meant cannot cut. And I have a friend named Tom. He is, therefore, a Tom, and you cannot cut him either. But we didn't understand atoms until 1897. That was when it really began. They kind of thought atoms were these billiard balls. Whoop. And then suddenly we realized that the Greeks were wrong because Thomson cut an atom. He discovered the electron, and the electron was a particle that was fantastically less massive than an atom. For the simplest atoms that he was studying, this electron, mass of the electron, was, well, it's always less than 1/2000th the mass of an atom. Wow, that's a very tiny mass. Okay, so he also really liked pudding, and he would have his pudding with plums in it. And apparently, in England, plum pudding is much like a blueberry muffin. If you get a blueberry muffin in the United States of America, the blueberry muffin's like this, and inside of there are some blueberries. There'll be like a blueberry here, and a blueberry there, and a blueberry there, and a blueberry there, and a blueberry there. Now, I've never had plum pudding, and I gotta be honest with you, it doesn't sound wonderful. Correct me if I'm wrong. If you live in Great Britain and you like the plum pudding, talk to me, because I just don't know what it's all about. But a blueberry muffin is a fine thing, and Thomson said there are electrons inside of blueberry muffins. I mean, this is a metaphor, you have to understand. It's as if the electrons in an atom are like the blueberries in a blueberry muffin. There's a whole bunch of muffin where there aren't any blueberries, and then there are some blueberries, and the blueberries are the electrons. So Thomson knew that atoms were neutral. So he knew there had to be positive stuff and they knew there had to be negative stuff. So he said the muffin is positive. Muffin is positive. And he said the blueberries are negative. Somehow, there was just enough negative as there was positive, but he found that the negatives were concentrated at tiny little points because he had cut them off. He'd sliced off electrons. That's kind of cool. Now, enter Rutherford. Rutherford was described as the greatest experimenter since Michael Faraday. That's quite a compliment. He was also born in New Zealand. You need to know that about him. So what are we talking about? We're talking about 12 years after Thomson discovered the electron. 1897 to 1909, the experiment was done. Marsden and Geiger did the experiment in Rutherford's lab under his direction. And then in 1911, Rutherford published, his explanation of how everything went down. First, he said pudding has no place in science, and secondly, he observed that everything was really weird. His experiment went like this. He had, for lack of gold, I actually have to use orange, but he had a gold foil. Now, you want to try to figure out why he used gold? You think about that for a minute. But his gold foil was such that it was just one atomic layer thick. Dang, that's amazing. And he took a source of alpha particles. He had already proven, I think it was 1907 or something, he proved that, let's see, this is a source S-O-U-R-C-E, source of alpha particles. He proved that alpha particles were helium nuclei. Helium nuclei. Helium nuclei. So we're talking about a proton and a neutron and a proton and a neutron. Standard helium-4 stuff. You've got this particle here, and he could send them out of a box going really fast. I don't want to talk about how he got it, but there's this little thing, and it's essentially a 2+ thing shooting that direction. And it is incredibly massive compared to the electron. He had measured these things were like 8,000 times the mass of an electron. And he's shooting it at the gold foil. And I can't understand why he would do this experiment, because this experiment seems absolutely stupid. He already knew, well, from Thomson, he knew that there was a goo of positive in here spread throughout the gold, and then there was little specks of negative that had very, very little mass. And so when he shot this through, maybe he was trying to study the electrons in greater detail. I guess if there are some electrons in there, remember we called those guys blue, then you might find a very, very tiny bending of the path of this positive charge coming through here. You think maybe if it goes particularly near an electron, it might do something like, instead of going like this, it might do something just barely like that. And he put a detector over here, and he wanted to see where these particles were going. So that's fine, but the second question is, why did he do this next thing? Why did Rutherford do this? Why did he do this? You ready to find out what he did? He took his detector and he brought it over to the other side. He brought his detector back around to the other side, like over here and over here and over here and over here. And lo and behold, he was getting reflected alpha particles off of the gold foil. This was absolutely stunning to him. So my question is, why did he do it? I don't know. Really fascinating story though. He described the firing of these really high energy double-plus charges at a smearing of gold foil. This is just one atom thick, and he's firing these really fast moving things at it. He described seeing those things hit the foil and bounce back being equivalent to firing a 15-inch shell. Now, I'm not a big fan of inches, but this sucker is something like, wow, I guess that must be like 0.4 meters. A 0.4 meter shell, a projectile, at a piece of tissue paper here. He's described this as being the same thing as firing an enormous projectile at a piece of tissue paper and having it bounce back at you. It was that stunning to him. He fires these really, really heavy things really, really fast at gold foil, and he found some coming back this direction and that direction and that direction. It was very, very few of them. Very few were reflected. But those that were reflected were freaking reflected. There was no other way for the alpha particles to get back there. So he was tracing their path, and he calculated the percentage that had gone through and the percentages that were reflected back, really crazy. And he said, you know what, every once in a while, I'm getting pretty close to something that is really, really, really big inside of this gold foil. And those things that are really big inside the gold foil are not very common. But every once in a while, there's these things in here that are causing my alpha particles to bounce backwards as if they'd hit something much heavier than themselves. Dang, it's like a bouncy ball running into a charging rhinoceros, right? Can you think about that? It'd be like, wow, bam! So what happened was, Rutherford was thinking about it for 2 years. It was 1909 the experiment was done. In 1911, he said, I think there's a nucleus. So I think there's some positives in here, and for gold it was like 79 or something. It was like a whole bunch of positives in here. And he said, that's really concentrated, and if we make this the size of the sun, just to give you an idea of how strangely shaped this atom was that he was thinking about. If this is the size of the sun, you remember that dwarf planet they call Pluto? Pluto's like way out here. And I don't mean that because this is just a terrible scale here. Pluto's orbit is way out here. Let me try again. All of these positives are supposed to be the sun. And so I'm going to say the sun is about this big right here. And then out here, no, that's way too big still. Out here is the orbit of Pluto. Way out there. And he's saying that The positive charge is concentrated at such a tiny spot right here, and he calls it the nucleus. He says, up in here, that's where all your positive is. And your electrons are still, you take your Thomson model, there are still some electrons floating around here, but there's not a smear of positive. See, Thomson thought positive was all over the place right here. But Rutherford says, I'm firing these things, these really, really, really heavy alpha particles. He's firing alpha particles that direction, and most of the alpha particles don't do anything. They just go straight through. And every once in a while, one of the alpha particles comes in just right so that it goes What? What? And these guys right here are extremely uncommon, but that means that he could estimate the size of the nucleus. And he found that the nucleus was smaller. Whoa! The nucleus was smaller than the sun in terms of the electrons being out of the orbit of Pluto. That means that the atom is almost entirely empty space. You are empty. Sorry. The atom is almost entirely empty space. And it means that there's an extremely concentrated positive here, and there are some electrons that are floating around here that can also be scraped off. This makes sense. The electrons could be scraped off more easily if they're out there. Here's the only problem. He said that the nucleus is positive. So I got a nucleus that's positive, right? And I don't care that it's just one charge right there. And then there are these electrons that are going around it. Now the electrons are going around in orbits. And the problem with an electron going around in orbit is if you are going in a circle, then you must accelerate towards the center. And this is a small problem. What do you want to call this? Centripetal acceleration? We could say AC is VT square over R. He did some calculation for how fast it would go, because you could just use the electric force. And what are you going to get? Kc times q1 times q2 over the distance square. He knew this distance, he knew the charges, and he figured out what the electric force was, and he set that equal to mass times centripetal acceleration. He said these guys are circling around at this speed with this acceleration. The only problem is that when electrons accelerate with the acceleration that he calculated, they would emit radiation. In fact, they would lose energy so fast that within a microsecond they would spiral into the nucleus, and, that radiation would annihilate everything in a flash of light, which would be rather problematic. So there was another bit of experimental information that Rutherford had to deal with, which is stuff still exists. That's a very important fact to deal with, and so let's continue on and see how people dealt with this. But Rutherford was a really smart experimentalist, but his theory, what the heck? His theory says everything's going to collapse on itself in less than a microsecond, but he took 2 years to do it, which is substantially more than a microsecond. So what gives, Rutherford? Stuff exists. I don't know. We'll see what we can do to solve this problem. We might need quantum. So it's been agreed by many scientific bodies that the most important sentence, if we could pass on one thing to another culture, it would be all matter is made of atoms. That this sentence is the most important thing. So we have to understand knowledge forward. Every one of these things that we'll discuss today was a silly mistake, and sometimes utterly ridiculous. However, that's the course of science. It stumbles around for a bit and gradually converges closer to the truth. We have to believe that, and we have to believe that every process in science, no matter how stupid, is useful and brings us towards the truth. As long as we're honest and competitive with each other's scientific results, you keep trying stuff and you get to the answer, what atoms are and why this is so important. The ancient Greeks, the ancient Greeks had a they had a word that means cannot cut. It was atom, and MC Hammer, actually, a lot of people don't know this, but his song was originally... Welcome to another issue of the soap opera of science. It has been decided, first of all, let me say that we're going to talk about a lot of people here, but I want to make sure that you understand we're honoring these people because they brought